Hello, in this video we're going to be reviewing conservation of energy, one of the most fundamental backbones of physics. This is a material you should be pretty familiar with from your pre-IB science work, but we will be going over those pieces and kind of talking how to set up a basic conservation of energy problem. All right, this is one of the most fundamental parts of physics. There is almost any field of physics you can apply conservation of energy to and understand by applying this law. It is maybe the most universal law of physics that we have. We can use it to explain new phenomena. It still today helps us make new testable predictions. It is really a big deal. So we're going to do a lot with it. Energy is the one thing that probably comes up more than anything else throughout all of IB physics. So no matter what unit we're looking at, when we're talking about electricity and magnetism, we're going to be talking about energy. When we're talking about nuclear physics, we're going to talk about energy. When we're talking about astrophysics, we're going to be talking about energy. So it's really everywhere. All right, of course, we're going to go over the two types of energy, kinetic energy being the first one, and this is energy of motion. You know and love it. 1/2 mv squared is kinetic energy. We use E sub k in the data booklet. The unit of energy is the joule, spelled like so. We use capital J for the joule. And a joule is a derived unit, so it must be a kilogram meter squared per second squared. Just think 1/2 mv squared. 1/2 is just a number, it's got no units. M would be kilograms. V is meters per second, so V squared, meter squared per second squared. All right, M is the mass of the thing moving that has the energy, and V is its velocity. Do notice V is squared, so even though velocity is a vector, kinetic energy is a scalar. You can't have negative kinetic energy. And we have gravitational potential energy as our other type of energy. And this is energy that has to do with location in a gravitational field. It is considered stored energy. When we say potential, that's what we mean. So if I hold an object up above the ground, I say it has potential energy because potentially if I let it go, it would gain a bunch of kinetic energy as it falls to the ground. The data booklet gives an equation that's maybe slightly different than what you're used to because we're being a little more technical here. That really what we're looking at with potential energy is a change in gravitational potential energy. Or that's all we can ever really look at, but we're dealing with the change. And so we're dealing with a change in height. So you might be used to just MGH. We'll look at that and you can more or less get away with that most of the time. But really you want to keep in mind that potential energy is always relative. So it's all about a change. So we have a change in potential energy. M again is the mass. G is the gravitational field strength or the acceleration due to gravity, however you want to think of it, at the location that you're doing this. Delta H is the change in height. This assumes that obviously we're in like a uniform gravitational field. So these work near the surface of the planet. Once we get to space and we start doing some field stuff, we will have to modify this a little bit. So here's the idea behind gravitational potential energy in this relative point. For sure, we say moving up, you have more potential energy because you're storing more energy in the gravitational field, whereas moving down, I have less potential energy. You choose where gravitational potential energy is zero. You can really choose it anywhere in a problem, and you want to choose it at a point that makes it convenient. So usually, we're used to saying, there's zero potential energy on the ground, or there's zero potential energy on the surface of your desk. But if you decide to say there's zero potential energy on the floor, well, what if you're on the second floor? What about the classroom below you? So they're choosing their floor as zero, and that's fine. It works both ways because we only care about a difference. So the zero is kind of arbitrary. You want to keep it in mind. It will sometimes come up and be important when we start getting more involved with this stuff. So here's a way we can think of this change. If I am talking about a change in potential energy, what I really care about, if I'm throwing a tennis ball in the air, it starts at some height, it ends at some height. I care that it gains potential energy. And so I really care about the change in potential energy. Remember, in physics, delta means a change. I can always do the final value minus the initial value. So if I want to find the change in potential energy, I can do final potential energy minus initial potential energy, mg final height minus mg initial height. We can see that that change does work out to be mg delta h. This is kind of why. And if we take that one step further, if I want to call the ground 0, right? If I call the initial height 0, then my initial potential energy is 0, and so I get the potential energy at this point relative to 0 is mgh. So this is why we say potential energy is mgh at a point, because we're assuming the ground is 0, and we've defined that. So as long as we define the ground to be 0, you can get away with this. So most normal conservation of energy problems, this is fine. Just using mgh is fine. You do want to keep in mind, though, that really we're doing mg delta h. That's the more technically right way to do it. So just be wary of this whole 0 thing, and that we're really looking at a change. So you need a relative reference point. All right, so setting up conservation of energy problems is super simple. The idea is that total energy is conserved and does not change. So the idea is that no matter what 2 points I pick in the course of something happening, if I have an isolated system, then the initial energy and final energy will be the same. The one important assumption we're making is that there's no resistive forces. Something like friction would take energy out of my system, and I would have to deal with that. Of course, you've heard no energy can't be created or destroyed. So even friction isn't destroying energy, it's just like dissipating it as heat, but it becomes no longer useful to us and it leaves our system. So we need an isolated system. And really we just set the total initial energy equal to the total final energy in the basic version of these conservation of energy problems, which is what we're kind of reviewing here. And here's what that usually looks like. We have 2 types of energy that we mostly care about, at least at this point, kinetic and potential. And so we take the initial kinetic energy of all of the objects in the system, the initial potential energy of all the objects in the system, the final kinetic and the final potential of all the objects in the system. So keep in mind, if there's 2 objects, you might start with 2 kinetic energies, and you might end with 2 potential energies, so it really depends. We will be adding more to this. This doesn't take into account if any work is done, if there's a change in energy, anything like that, in terms of external factors. So here you can see a straightforward example where we are doing the classic drop a stone from a certain height, let it hit the ground, and how fast is it going? In this case, we can look at the whole conservation of energy equation just to see mechanically how this equation works. But really, pretty quickly, you're going to get used to just being able to look at these problems and saying, okay, it starts up at some height, it's at rest, so it's got no kinetic energy, so it has all potential energy. And then it falls, accelerates, speeds up, hits the ground with some speed at a height of 0. We're going to choose to call that 0 joules of potential energy to make our lives easy. And so it's all kinetic. So it goes from all potential to all kinetic. So no big surprise, I go from mgh to 1/2 mv squared. Mass cancels out, which happens almost all the time in these conservation of energy problems, unless they have, say, elastic energy or work or something. I solve for v, and I get square root of 2gh. This is something that you may have seen in kinematics problems. You would notice you could solve this problem with a kinematics equation. You could use the equations of motion, do some suvat, you'll get the same exact answer. You would even get square root of 2gh, which is pretty amazing. All right, there's a lot of ways to solve a lot of these problems. Conservation of energy tends to be an easy one, but lots of ways to tackle many of these problems. All right, so this is just a quick warm-up for you, a refresher of the types of energy. We will dig into it in more depth very soon. Have fun.